All right, in this video, we're going to go over two of the questions from your Chapter 11 review, the first two questions. So they give us this story about contract tracers, and what really matters here, the question says, given that the median is much smaller than the mean, what can we assume to be true about the shape of the distribution, left skewed, symmetric, or right skewed? And so here's how I would answer that question here. I just typed it rather than making you try to watch me write here with my stylus. But the whole idea is that the mean is not resistant to extreme values. So if we have a few states whose rate of contract tracers is much higher, that would skew the mean towards the extreme, while the median would not be changed. So what's happening here, if we kind of draw a rough probability distribution here, or histogram, we've got our median, which is 7, and then our mean, which is 12. So the median is going to be where our peak is roughly here. And then we've got a few states who have a number way over here. And that pulls the median up. Most of the states, because what we're counting here on the x-axis is number of states. And that's the y-axis. The y-axis is the number of states, and then the x-axis is the contact tracer rate. And so what we're counting is how many states have that many contact tracers. So as the number of contact tracers is counted for each state, you're going to have a few states that have very few. Most of your states are going to have around 7. That's our median. And then we've got a few states who have 8, 9, 10, 11, 12. But because the mean is, so that's the average, the mean is 12, that means there's a few states who are way out here that's pulling that number way farther than the median. Whereas maybe you've got a couple states that are low, but that's not, that difference between this low and this high is not as extreme, because when you take the median, 7 is in the middle, regardless of whether that biggest number is 12 or 1,000. 7 is just in the middle. But the size of that bigger number makes a difference when you calculate the mean. So because the mean is larger, that mean is literally being skewed, pulled towards these extreme values in our distribution. Okay, so that's the first question. Now the second question, there's a lot more to do, and so once again I just copied my typed answers here, but then I wanted to be able to kind of walk us through what I think this should look like here. So first of all, it asks us in the question, do I have the question stem? No, I didn't copy the question, but what it asked us to do in part A was to create a probability distribution for each exam. So we've got German on the left, physics on the right, and the probability distribution, I asked you to format it a particular way. You've got each possible outcome, so you can get a 1, a 2, a 3, a 4, or a 5, and then the probability of that happening for each exam. To find these probabilities, of course, what I'm doing is I'm just taking, 364 ones out of the total number, and I'm just adding this all up and saying, okay, what's the probability that I get a 1 on the exam here, and same for all the others, and same for the physics as well. To calculate this mean, standard deviation, and median, to calculate all three of those, you're going to want to use your calculator. And what you're going to want to do is you're going to want to make the possible outcomes here L1. So you go to your stat edit, type in L1, 1, 2, 3, 4, 5, and then in L2, type these numbers next to it. And then when you go to your 1var stats, it's going to ask you what's your X list. So your X list is L1. But then it's going to ask you for your frequency list. And make sure you put that in as L2, frequency list. Oops. Frequency list, L2. Because what that does is it tells the calculator, yeah, I want you to find the average of the numbers 1, 2, 3, 4, 5. But really, I want you to find the average of 364 ones, 854 twos, 1,149 threes, 826 fours, 304 fives. We're telling it how frequently we saw a 5, how frequently we saw a 4, and so on. And then the calculator is just going to give you these values. Make sure for the standard deviation for this problem that you're using the population standard deviation, which the population standard deviation is the sigma. Not the S. The S is for sample, and that would be if we had, a small sample of the German language students or a small sample of the Physics 1 students. But we don't. We have all of them. We have the whole population. So make sure you choose that population there. If you look at the first one, it's not perfectly symmetric, but between the three choices of symmetric, left skewed, right skewed, symmetric is by far the better option for German. I mean, you can see we've got significantly more threes. The numbers of twos and fours are roughly the same. The numbers of ones and fives are again roughly the same. We've got a few more twos than fours, a few more ones than fives, but you can see, I mean, the difference between a 1 and a 2, a 4 and a 5, those are, roughly equivalent. So you're going to have more or less for German here, kind of a symmetric, nice pretty bell curve here, much prettier than what I just drew. Symmetric on both sides here. It's way more symmetric than it would be left skewed or right skewed. And the other thing that we see there, like we saw in the previous question, is the mean and the median are almost the same. 2.958 and 3. Those are really, really, really close to each other. So there's not been much skewing of the mean away from the median. And you can see it is a little bit less because there are more ones than there are fives. There are more twos than there are fours. So we are very, very, very slightly left skewed. Left skewed because we're pulled that way towards the left. But it's mostly symmetric here. And then for the physics one, same deal for all these numbers. But now we're skewed to the right because the mean has been pulled farther to the right than the median. So we're skewed a little bit to the right there. And if you drew that distribution, you would see a tail on the right here. Okay. Then the question asks us, are we discrete or continuous? We're discrete because we can count the scores. Discrete is something you can count and you have an individual score. Continuous has to be measured, and you have to list the outcomes in ranges. You can't list the probability of an individual outcome. It has to be in a range. The formula for the z-score here, hopefully we remember that. Z is equal to whatever actual score you're looking for minus the mean over the standard deviation. So in this case, the question asks, what's the z-score of a 5? And so we would do 5 minus 2.958, which is the mean, over the standard deviation, which is 1.1148, and we would get that value here. And then for F, it's really the same thing. It's just a different part of the equation that we're looking for. It says in the original question, what score would produce the same z-score? And so we put that z-score of 1.832 equal to our z-score formula. No, not the 2 points. 2.511, the physics mean, over 1.238, the physics standard deviation. And you solve for x and you'd get that value there. And so the z-score there is a little bit lower. And what the z-score is showing you is how many standard deviations you are from the mean, which is essentially a measurement of how extreme a value is, how much different from the mean. And so to get the same amount of difference from the mean on the physics exam, you actually need a slightly lower score. Because on physics it takes 4.779, whereas on German it took a 5. And so, as I said here, you can't actually get a 4.779, but that's just showing that, okay, if a 4.779 has this z-score, then a 5 would have an even greater z-score, showing us that it's even more difficult to get a 5. And there's other ways that we could have seen it's more difficult to get a 5. You could just see it, but that's kind of what z-score is about here. Okay. So that's the first 2 questions on the review. There will be more videos for the remaining ones.